Tricarb System Overview Chapter 1. In this chapter, we'll cover the basic hardware modules of the Tricarb instrument. In subsequent chapters, we'll cover QuantaSmart software overview, system calibration and normalization, defining a count per minute assay, loading and counting samples, defining a quench standards assay, defining a disintegration per minute assay, and advanced features. The Tricarb instruments are completely computer-controlled benchtop liquid scintillation analyzers. The external Lenovo laptop running on a Windows 7 operating system controls all functions of the instrument, including programming of counting parameters, movement of samples in cassettes on the sample changer deck, counting samples, and displaying and printing sample information. The Tricarb liquid scintillation counter relies on the interaction between a beta-emitting radionuclide and a scintillation cocktail. The scintillation cocktail is made up of aromatic solvents and scintillators. The scintillator converts ionizing radiation from the radionuclide into photons of light or scintillations. The intensity of the light is proportional to the initial energy of the beta particle. By placing a vial containing a radionuclide and scintillation cocktail into the instrument's detector, the scintillation counter can measure photon intensity. Paired photosensitive devices called photomultiplier tubes amplify the light emitted from the sample and convert the light to pulses of electrical energy. These pulses are sent to analog-to-digital conversion circuitry for validation. Shown here is the block diagram of the liquid scintillation analyzer. The twin PMTs will send signals to the coincidence circuitry. If they arrive within 18 nanoseconds of one another, we consider the pulses to be from a radioactive event and not a noise pulse. The coincidence circuit will allow the analog-to-digital converter to open and accept signals. The twin signals will be summed together in the summation circuit and then digitized by the ADC circuit and placed into a multi-channel analyzer for storage and final data reduction. Communications to the Tricarb will be via an external laptop computer, which is provided and not an option, communicating through a USB port to the instrument. The system is controlled by an external laptop with a Windows 7 operating system. The laptop includes a CD/DVD writer, Ethernet connection, and 3 USB ports. The laptop is attached to the arm that may be mounted on either side of the instrument with a locked cable for security reasons. An optional feature is a two-dimensional barcode reader that provides automated sample tracking for the Tricarb system. To use the reader, a 2D barcode is placed on a sample's vial cap and the label is read before the sample is loaded. This view shows the back of the Tricarb system, both with and without the optional refrigeration unit. A minimum of 6 inches clearance is required for proper airflow. This view shows the connectors on the lower left side of the Tricarb system. The 2 USB ports are used for the external computer and the barcode reader. The right side system view shows a close-up of the power switch, power connector, and fuse holder. Again, a minimum of 6 inches clearance is required for proper airflow. Cassettes are the plastic racks that hold sample vials and allow them to be moved on the sample changer deck. Samples are placed into cassettes that accommodate either standard or small vials without adapters. The standard vial cassette can accommodate up to 12 15 to 20 milliliter vials, and the small vial cassettes up to 18 6 to 7 milliliter or 4 milliliter small vials. Additional size sample vials may be counted using adapters. A protocol flag, which you attach to the cassette, identifies the assay conditions that you've defined for use with your samples. The individual cassettes are identified by unique numbers, cassette IDs, located at the end of each cassette. The protocol flag and cassette ID are automatically read by the instrument to provide positive sample identification or PID when using work lists. Protocol flags are numbered plastic devices that contain an encoded reflective metal strip that the instrument uses to identify the appropriate assay counting parameters for a set of samples. The counting parameters that the instrument uses correspond to the settings that you define during the assay definition process. These assay settings become a functional part of a protocol once you associate the assay to a protocol number. Prior to counting samples, you must attach the correct protocol flag to the first cassette of the samples to be counted. When the protocol number is recognized, a reset flag indicates that the assay is being counted for the first time. The system will automatically set the flag after the cassette has been counted. Subsequent counting of the protocol is considered to be the following cycles of the same samples. You should reset the protocol flag each time that you put new samples into the cassette.